Hello and welcome to this extra lecture for the Brazilian ICPC Summer School of 2022. This lecture I'm going to talk about parsing, but it's not going to be a full lecture, but instead more like a walkthrough on how to parse expressions coming from a simple grammar using a recursive descent parser. So the goal is not to cover the whole topic, but just to show you the easiest cases that you can solve, which are also the most common to appear in programming competitions, so that the next time that you see a problem that involves parsing expressions, you don't just avoid solving it because you're afraid of parsing the input. So that's the very modest goal I have today, and hopefully you will learn to do this very quickly and very efficiently. So first, let's talk about grammars. So a language is defined by a grammar, and this grammar is just a recursive set of definitions of the terms that construct the objects or expressions in this language. So for example, you can have some expression that is defined as one of various options. So it can be either an option, let's call it 1, or option 2, or many more options. Now then you can have each of these options, let's say option 1, can be defined in terms of other options, right? And each of these things that you have here, either one or the other, or more if you have them, can in fact refer to other definitions. So for example, this one could point to an expression, or this one can point to some other option defined below. So the grammar is a recursive set of definitions, and applying this recursion following the options will generate different expressions in this language. The task is to decide, for example, whether an expression is well formed. That means whether the expression can be generated from the set of rules that is in the grammar, or if your expressions involve terms that can be interpreted as a computation, then you may want to evaluate the expression, which means to perform the computation and obtain a result. So let's see a very simple example to make sure we understand this. Consider, for example, this simple grammar with just one rule, which has an expression to be defined as either the empty string, or if we say that string concatenation, we denote it with a plus sign, we take a parenthesis opening plus an expression plus the closing parenthesis, or you could say that is an expression plus another expression. So you see, this simple rule already has this recursive property. And for example, let's say that we want to make a list of the various expressions that this grammar can generate. We have, for example, applying this rule, that an expression, or the set of expressions, contains the empty string. What else can we generate? Well, if we then apply the second rule here to the expression that we already found, we see that this, the opening and closing parenthesis, is also an expression. But applying it again to the same thing that we just obtained, we could see, for example, that this is also an expression. Now, we can continue like this, but we can also try to apply this rule. So we could apply that rule to, for example, the second and third expressions that we found, and then we would obtain an expression like this one: open, close, open, open, close, close, Or we could apply it in the different order and say open, open, close, close, open, close, and we have a different expression from the concatenation of the two that we had before. And we can continue like this, and in general we will obtain some parentization, some string that is a valid parentization. That means it has opening and closing parentheses in a valid way. For example, we can apply now the first rule to the last thing that we obtain, and we open, then we do two open, close, close, then another open, close, and close, right? And this goes on, and there's obviously an infinite number of expressions that this grammar generates, but they are all valid parentizations. So one question would be, given a sequence of parentheses, for example, if I say this sequence, is it a valid expression generated by this grammar? Of course, the answer to this question cannot be let's generate all expressions, or it cannot even be let's generate all expressions up to a given length, because if your input is long, then you will have to generate potentially a large number of expressions. So you want to write a parser which actually reads this expression and somehow moves along the definition, trying to match in which option you are dealing with at each point. And if this parser succeeds in parsing this expression, then it will mean that this expression can be generated by our grammar. Instead, for example, a parser would never be able to finish parsing an expression like this. So we know that every time that we put an expression with parentheses, we put the same number of opening and closing parentheses. So while the left-hand side here can maybe be an expression, and you can actually see it is, the right-hand side here is definitely not an expression, because there is not the same number of opening and closing parentheses, and we know our grammar adds one opening and one closing parenthesis whenever it adds some parentheses. So you see, when the grammar is very simple, maybe you can tell beforehand, and you can write some other conditions that need to be met so that an expression is valid. So for example, this term does not have the problem of having different number of opening and closing parentheses, but has them in an incorrect order. So this is clearly also not a valid expression generated by this grammar. Well, you can think of conditions that rule out some potential strings from being generated by this grammar, but it's better if you can actually write a generic parser that reads an input and finds whether this string can be generated by the grammar you provide. So the whole point of this lecture is to try and show you that for simple grammars, where you can decide rather easily which option you are taking in a given rule, it's not hard to actually write the parser, and you can then answer these types of questions. Or if you have a model for what the terms, the operations in your grammar mean, then you can also evaluate this expression. So parsing and grammar in general are very large and broad topics, but in ICPC problems you usually have just two cases. So first, some problems involve just parsing. So sometimes the problem is to parse the expression, maybe to say whether it's correct or not, whether maybe it's to evaluate an expression given a set of rules of how to compute what each term means. But just parsing problems are something that sometimes appears. Sometimes the algorithm after you parse is very simple. So in these cases, parsing can be the main obstacle. These are not so common, but sometimes it's the case, and it's important that you know some parsing technique and that you are confident with it, so that these problems don't scare you away. So this is one type of problems. A different type of problems are just more involved, so they involve parsing before doing some other algorithm. So in this case, sometimes, so the grammar is given, So sometimes here you just are given a grammar explicitly. So you have an explicit grammar that defines the input, and the question is not really how to parse, but you know what you need to do after being able to parse this expression. Instead, in the just parsing case, normally the grammar is not given. So that means that you need to figure it out, right? So it's not in the problem statement. You need to actually write it down yourself and make sure that what you interpret are the rules that the problem statement is giving you is properly translated in formal terms. So let me show you what I mean by considering a slightly harder example, which involves mathematical expressions. So let's define a grammar for algebraic expressions. In this grammar, an expression will be defined as either a term or an expression plus the plus sign plus the term, or the expression plus the minus sign plus a term. What is a term? A term is defined as either a factor or a term plus the multiplication sign plus a factor, or a term plus the division sign plus another factor. Now, a factor is then defined as a number or the parenthesis plus an expression plus the closing parenthesis, and we have to define the number, but let's say that to avoid just a long definition, we all know what a number is. Let's say it's a natural number, a sequence of digits that does not start with 0. So this is a grammar that defines algebraic expressions such as, for example, 4 plus 8 times 7 minus 6. And one thing I want to stress is that this definition encodes certain properties of these operations, because you can think that these operations, the plus, the times, and the minus, these are inside a string, but you can also think that these actually evaluates to 4 plus 8 times 7 minus 6. So 8 times 7 is 56, minus 6 it's 50, plus 4, this should evaluate to 54, right? Well, in order for that to be true, for example, we had to make sure that these things are evaluated first, and then the terms are added in the correct order. And in fact, this is encoded in the grammar by saying that, for example, here an expression is the left part plus and one last term. So in this case, the terms are to be evaluated from left to right. So this is left associativity. So in fact, what I should have done is 4 plus 8 times 7 minus 6 in that order. Now, there is also left associativity here, right? There's a term which goes first, the times, and then the factor, and this would be important in determining, for example, what an expression such as 2 times 3 over 6 means, especially if you're using integral division. So it's important to know how the grammar actually encodes the properties in this case left associativity, but it can encode many different properties of your expressions, which affect the results if you actually think about evaluating these expressions. Now, it's important to know this and to be aware of this, so that when you have a description and the description says expressions are to be evaluated maybe right associatively or left associatively, you know how to write the grammar in one way or another. If I wanted to write, let's say, right associatively for this grammar, I would instead, for example, say that the term is a factor plus the multiplication sign plus a term. And then evaluation would go from right to left. So, in conclusion, you should not rely on the problem statement giving you the grammar. Sometimes it just gives you a description of the grammar and you need to translate the description into a formal grammar. But it's important to do this translation properly, to think about the properties that the problem statement says that the grammar has, and you will need the grammar then to write the parser. So I will now show you how from the grammar you can somehow extract essentially the parsing of that grammar, if the grammar allows for a simple recursive descent parser, which I'm going to assume it does. Good, so we are now ready to start describing how to write a recursive descent parser. Now, the properties of this parser are the following. It has three nice properties. First, it's easy to code. So you will see, once you have the grammar, coding the recursive descent parser is essentially following the structure of the grammar. It's not complicated, it's very straightforward, because if you have already written the grammar, you will define one function for each grammar rule, and this function will imitate what the grammar rule is saying, so it's really easy to code. Next, it's fast. So recursive descent parsers are OL, where L is the length of the string. So if you have an input of length L, it takes OL time to use a recursive descent parser to parse it and either evaluate it or decide that this is a well-formed or not well-formed expression. Finally, the third property, it's easy to extend. So sometimes you want to evaluate expressions, sometimes you want to check for errors. You can adapt this strategy, the recursive descent parsing, to any requirements that you have for your parser. So either evaluation or checking well-formedness or whatever you want to do will be very easy to change just maybe the return types of the functions that you write and adapt to one case or the other, or set some flags for errors. It's very, very easy to do these things and maybe modify them. So you can maybe sometimes start by creating a parser that checks an expression, and then you want to evaluate it. You just modify a few bits here and there, and you're done. So these are the nice properties that a recursive descent parser has. And now, what are its main ingredients? The ingredients that you will use in any recursive descent parser are two. So first, you will have a global input string, which will have the string you want to parse. Second, it will have a global position pointer, which will be pointing towards the next position in the string that we are considering. So these two global variables are the key to writing a recursive descent parser, and they are essentially the gears that you will use in your functions to move through an expression. Let me show you with an example, and in particular, let's start writing a parser for the grammar for algebraic expressions that we wrote before. So, before we start, what we need to do is define each of the ingredients that I said we had to put in our parser. We have a string or array of characters in C++ that gives us the input expression that we want to parse. So this I will think as an array where the first position is 0 and the last position is L minus 1. And this is globally defined, so it's outside main. Then what we have is this position pointer, which will point to some particular position within our input. So the input will be read first, position will be initialized to 0, and as we parse, the position pointer will move around. The next ingredient is a function for each definition in our grammar. So here I have functions to read expressions, to read terms, to read factors, and to read numbers, because those were the 4 definitions in our grammar. And I'm defining here the type or tint just for convenience. In this case, I'm going to think that the expressions are working all with double precision floating point numbers, but if you want to work with integers or whatever your problem requires, well, you can easily define some type with which your grammar works, and then all functions, in this case we want to evaluate the expression, so all functions will return this type. Now, if you had some arguments to pass to these functions, maybe because you have some variable inside your expressions that may take different values and so on, you could put them either as arguments to these functions, or you can define them globally here. So these are 2 options. You can define more global variables that your parser can use. The minimum is 1 for the input, 1 for the position. If you have some more arguments, you can put them there, or you can make them proper arguments, which is usually better, just not to have a lot of global stuff. Anyway, the main point of this prelude is to see what you're going to later use, and let me point out that declaring the functions is sometimes necessary because the recursive structure of the grammar means that each function can depend on other things in a circular way, such that the function depends on itself, and then the compiler needs to know what these functions return at least, or the signature of these functions, at least in C++. So in any case, it's usually good practice to define the functions, to declare them before you define them, so that you know, okay, I'm going to have a function for reading expressions, 1 for reading terms, 1 for factors, and 1 for numbers. Let's move on now to how to write the first function that we need to write to parse an expression. Okay, so the first definition in our grammar was for expressions. And an expression was defined as a term, or an expression plus a term, or an expression minus a term. How do we translate this to code? Well, the key point is, first, there's always a term, because it's either just a term or an expression which will start with a term, or an expression that will be an expression that starts with a term, and so on, right? So because all definitions point to terms, then the first thing that we need to do is read a term. So to read a term, we just call the term function, which we haven't defined yet, but it's declared before and it will be defined later. So we can just call this function and assume that this function will move the position pointer until the end of the term. Then what's going to happen? We have to decide whether we just had a single term, or we had maybe a plus sign or a minus sign. So we just check if the next position is a plus sign or a minus sign, and if it is, then this means that we are in one of these 2 cases. Then what we need to do is, first, we decide in which case we are. So here I'm using this sign function that is inline defined to choose whether it's a plus sign should go with a +1 factor and a minus sign should go with -1 factor. And after extracting this sign, I should move the position counter to the next position in the input string to mark that I have already taken into account, I have already parsed the plus or minus sign that I had seen. After parsing this, there should be another term, so I call the term function. I add to my result with the correct sign the result of this function, and I continue like this, so I have this while outside which continues checking for pluses or minuses until the next character is neither a plus or a minus. In this case, this will happen only when I reach the end of the string, because there's an expression is just a sequence of terms that ends when the string, the input, ends. So once that is done, I can return my result. So the first term was read alone, and all the other ones were added to that result. By the end, I have the final result of reading my expression. The way to deal with terms, to define a function that reads the term, is very similar. So terms always start with a factor, and then they can be multiplication signs and some other factors, or there can be division signs and some other factors, but always there's a factor first, and then I start by reading the first factor using a fact function, which I haven't yet defined, but it's declared and will be defined below, so it's okay. Then I need to check again. After reading the first factor, I assume the position has been moved to the first character after this factor has been read, and I need to check whether this character is either a multiplication sign or a division sign. So this case corresponds to this option, the multiplication case corresponds to this option. I'm showing you here a different way to deal with operations, so it's similar in spirit. You define some other function inline here to check whether the operation is multiplication or not, and according to this, you either multiply the result that you have or divide the result that you have by the result of reading the next factor. Now, it's important to notice that just like in the previous example, I have a while loop that processes the factors and adds them, in this case multiplies or divides them, to the result that I already have, and this goes from left to right. So here I am implementing the left associativity that I mentioned before. Now, if you had to implement right associativity, this is one of the things that you would need to change. In any case, the whole process, the while loop, ends when the next character is neither a multiplication sign nor a division sign. This can happen in our expression in two cases. Either I reached the end of the input, or alternatively, I could have reached a plus or a minus sign, which means that this term has finished, there's no multiplications or divisions, and I should read an extra term afterwards, but that's taken care of by the expression function to which this function will return. So all I have to do is, once I don't have any more multiplication or division signs, I return the result. So again, I follow the structure of my definition. In this case, I had one option, just one factor, another option, multiplication, and another option, division. I have these options in my definition of the term function. Okay, so before we use the fact function, which was not yet defined, we need to define it now. Now, a factor is either a number or an expression between parentheses. So what should I do? Well, I should check if the next position that I need to consider is an opening parenthesis. This case corresponds to an expression being between parentheses. Then what I need to do is first advance the position counter to take into account that I already know that this is an opening parenthesis and the expression starts just after this. Then I read my expression using the expression function, which is already defined. And later, I need to take into account that I know there should be a closing parenthesis. So the first position plus plus is increasing the counter for the opening parenthesis. The last one is taking into account the closing parenthesis. So this is one option. If we have parentheses, then we know we have to read an expression between them. Alternatively, you have a number. If you just don't have a parenthesis, then you should assume the next thing to read is a number, and you call a number function, which again we haven't yet defined, but we will define just after this slide. In any case, by the end, we either read an expression between parentheses or a number, but we have a result which we can return. Good, so the final function that we need to define is the one for reading numbers. I didn't give the explicit definition in my grammar, but let's say, to make things interesting, that we are reading floating point numbers. One way to deal with this, which is very nice, is to use a parser already in your programming language to do the job of reading the number. Otherwise, you need to read each digit, maybe multiply by 10 and add the next digit and so on. But in fact, your language of choice probably has a parser implemented so that you can parse numbers from strings. In C++ or C, you could use scanf function, which takes as input a C string and then essentially reads the number according to standard definitions. So let's say that our number can contain digits from 0 to 9 or potentially a decimal point. So we define a function in line that will check whether a character is valid, that is, can belong to a number. So this function will give you true if you have a decimal point or a valid digit, but it will give you false, for example, if you reach a parenthesis or a plus or minus or a multiplication or division signs. And we will use this function to put all these characters in a temporary buffer string, TMP. The point here is we want to advance the position counter with each character that we read, and we will put all of these in this temporary buffer, which later with scanf we can use to read the number directly. So this is just a trick to avoid doing the whole thing yourself. If you wanted to check whether the number is well formed, well, you can check the output of scanf, and by the end you should have your result set in this variable and return it, and this will be used by the function that called this, which was the factor function. So this completes the definition of our parser. Now all the functions are defined, they are recursively calling each other, and if you see, the position counter is just increasing. There's a finite number of characters that we ever look ahead, which is a condition to write the recursive descent parser. But these two facts also tell us that our algorithm is clearly O number of characters that our input has, because each character is essentially moved to the already read part of the string only once, and you only look ahead maybe one character forward. Good, so this essentially concludes this example. What we have to do to parse an input and maybe evaluate it, if this is the problem, this is all you have to do. Just write the parser, read the input, initialize the position pointer to the first character in the string, and later just call expression. This will return the result of evaluating the full expression. If you were to check for errors, you could set flags whenever you find some error. For example, you never find a closing parenthesis or these kinds of things, or you find a number with 2 decimal points. All of these things can be checked. You can add flags. You can have these expressions depend on external parameters. As I said, you add arguments or global variables, and you can complicate things, but essentially this is all there is to parsing. You just have to write the grammar, make sure that you understand the properties of the grammar and how to translate them to code. So I think this example should be enough for you to start tackling parsing problems. With that being said, I hope that this will help you solve some of the problems also that I proposed during the contests of the first week. If you have any questions, remember you can email me since we don't have any more Q&As, but you can still email me. And I hope that this extra lecture or short walkthrough through parsing has been helpful, and I encourage you to try some of the problems like tough water level and so on that maybe didn't get solved during the contest. Now you should be able to solve them.